guys. So today in this lecture we will learn about isomerism in organic compounds. So all of you know what is isomerism. This iso means same. This mer means is the parts are equals. So what is isomerism? It's the same molecular formula but different in physical and chemical properties. So that phenomenon is called as isomerism. So isomerism, the same molecular formula but having different physical and chemical properties. So what are the types of isomerism? There are two types of isomerism, structural isomerism and stereoisomerism. It's mainly two types of isomerism. Structural and stereoisomerism. So structural isomerism are chain isomerism, position isomerism, function isomerism, metamerism, and fifth one, tautomerism. And stereoisomerism are two types: geometrical isomerism or cis-trans isomerism, and second one is optical isomerism. So this is for type of isomerism in organic compound. So that organic compound having same molecular formula but having different physical and chemical properties. So mainly two types: structural isomerism and stereoisomerism. So structural isomerism are chain isomerism, position isomerism, function isomerism, metamerism, tautomerism. And stereoisomerism are two types: geometrical isomerism and optical isomerism. So geometrical isomerism or otherwise is called as cis-trans isomerism. So now we will see structural isomerism one by one. So first one is the chain isomerism. So chain isomerism having same molecular formula. So isomerism means same molecular formula but different in the order in which the carbon atoms are bonded to each other. Example, this N-butane and this is isobutane. So this is an example for chain isomerism. So what is chain isomerism? Same molecular formula but having different physical and chemical properties and arrangement of carbon atom is different. So this example for N-butane, isobutane or otherwise N-propane or isopropane, butane, propane. So like this you have to write it in any example. Same molecular formula but different physical and chemical properties and the arrangement of carbon atom is different. So that is called as a chain isomerism. And the next one, position isomerism. So position isomerism, same molecular formula. So the isomerism means same molecular formula. So position isomerism, same molecular formula but differ in the position of functional group on the carbon atom. So example, So functional group. So 2 bromo 1, 2, 3, 4 is a butane. Here 1 bromo butane. So butane, propane or pentane are the example for position isomerism. So same molecular formula but position of function group is a different. So function group position is different. So that is called as a position isomerism. And the third one, functional isomerism. So same molecular formula but different functional group. Example, so ethanol or ethyl alcohol. So dimethyl ether. This is an example for functional isomerism. So same molecular formula but that properties, physical and chemical properties are different but different functional group. So functional group is aldehyde, here functional group is ether functional group. So ethanol or ethyl alcohol or dimethyl ether. So that is an example for functional isomerism. And the next one is metamerism. So this type of isomerism is due to unequal distribution of carbon atom on either side of the carbon atom. So example, either side of the functional group, unequal distribution of carbon atom. Methyl, propyl, so 3 carbon atoms. So methyl, propyl, ether. So the functional group is ether here. So unequal distribution of carbon atom on either side of the functional group is called as metamerism, and this is diethyl ether. Diethyl ether. So that the molecular formula C4H10O. So same molecular formula but different alkyl group is called as an example for metamerism. So the metamerism is that unequal distribution of carbon atom on either side of the functional group is called as a metamerism. So that are called as structural isomerism. So what are the structural isomerism? So first one is a chain isomerism, second one is a position isomerism, and fourth one is a functional isomerism, and the last one is a metamerism. So chain isomerism, same molecular formula but different in the order in which the carbon atoms are bonded to each other. And position isomerism, same molecular formula but different in the position of functional group on the carbon atom. And the functional isomerism, so the different functional group present on the carbon atom, the carbon chain. But the same molecular formula is isomerism, means the same molecular formula. And that metamerism is unequal distribution of carbon atom on either side of the functional group. Our members are belong to the same homologous series. And the next one is stereoisomerism. So stereoisomerism are 2 types, so geometrical or cis trans. So stereoisomerism, so cis trans or geometrical isomerism. So cis means same ligands are arranged adjacent to one another. Adjacent to one another are called as a cis. And what is a trans? The ligands are arranged opposite to one another. Same ligands. Ligands are same. Same ligands, but arrangement are opposite to one another. So that is called as a cis and trans isomerism or geometrical isomerism. So same molecular formula, same structural formula, but different spatial arrangement is called as stereoisomerism. So cis isomerism or cis means same ligands but adjacent to one another. Trans means same ligands but opposite to one another. So example. For cis, so same ligands are adjacent to one another is called as cis isomerism. Whereas a trans isomerism same ligands is opposite to one another is called as a trans isomerism. So this is geometrical isomerism or cis trans isomerism. So same ligands adjacent to one another is called as a cis, whereas the same ligands opposite to one another is called as a trans isomerism. And the next one is that optical isomerism. It is a type of stereoisomerism. They have the ability to rotate the PPL. So what is PPL? Is a plane polarized light. So an optically active compound can exist in two isomeric form, that is for that plus or minus. So when they rotate the PPL, we can get dextrorotatory or levorotatory. So that organic compounds are, whether it's a dextro or rotatory, identified by means of polarimeter. Polarimeter. So first we take the light source. It's ordinary light. It's a light source. We can get the vibration in all the plane. So vibration taking place many different plane. So vibration takes place in many different plane. When the same light source is passed into the prism, that is a lens, prism or lens, we can get PPL. It's a plane polarized light. So what is a plane polarized light? So vibration taking place at only one particular plane, either right side or left side. One plane, any one plane, vibration taking place at one plane, so that the PPL is enter into the organic solution. It's a sample solution. Then you can get the observer. So you have to observe with that sample solution. So the vibration is taking place at any one at particular plane. So that right side direction rotation is right side means is called as dextro, and the rotation is left side is called as levo. So the right side R is called as a plus sign and left side is called as a minus sign. So this is called as an optical isomerism. So that optical activity, that optical isomerism is determined by means of polarimeter. So what is polarimeter? When the ordinary light source is passed into that one. So the ordinary light source vibration taking place at many different planes, but it passed into the prism or lens, we can get the PPL. So what is a PPL? Plane polarized light, vibration taking place at any one particular plane. So the PPL is entered into the sample solution when any organic sample solution. So the vibration taking place if you're rotating right side means is called as a dextro-rotatory. So rotating left side is called as a levo-rotatory. So the example for optical isomerism, it is optically active compound. This is for dextro. So dextro is a plus sign and it's a mirror image. This is called as a levo-rotatory. So this is a dextro-rotatory is a plus sign and levo-rotatory is a minus sign. So this is an example for optical isomers or optically active compound. So that same molecular formula and same structural formula but different behavior towards the light is called as optical isomerism. So same structural formula, same molecular formula, but behavior towards the light is different. So that is optical activity and non-superimposable each other. There are two types of optical activity. That is object and mirror image are different, are called as enantiomers. So for example, what is enantiomers? It is A, M, B. You can get that mirror image. It is an object and there is a mirror image B, M, A. So that is an image. So we can get that object with the mirror image are called as an enantiomers. So that is for that isomerism in organic compound. So there are two types, structural isomerism and stereoisomerism. So structural isomerism are chain isomerism, position isomerism, functional isomerism, metamerism. And stereoisomerism are two types. So first one is a cis-trans isomerism or geometrical isomerism. And the second one is an optical isomerism. So cis-trans isomerism is same ligands adjacent to one another is called as a cis. The same ligands adjacent to opposite to one another are called as a trans isomerism. And that optical isomerism, so we can get that rotate the plane polarized light either right side or left side. When the right side means is called as a dextro-rotatory, left side means is called as a levo-rotatory, and then get the mirror image, that is object with image, and that is called as the enantiomers. So representation of three-dimensional structure. So it is a convenient way, two-dimensional drawing that represent a three-dimensional molecule on a paper. So there are three important methods. So first one, Fischer projection. And second one, Sahar's. And third one, Newman projection. There are three important methods for such a planar representation, that is for the two-dimensional drawing that represent a three-dimensional molecule on the paper. So first one is a Fischer projection, you can see one by one. So Fischer, Sahar's and Newman. So first one is a Fischer projection. So now we represent the Fischer projection. A, B, C, D. So there are different atoms. Here is a towards observer. And behind the screen, it's a horizontal line, horizontal bond. And it's a vertical bond. So the Fischer projection is represented plus side. So one is that vertical bond, another one is that horizontal bond. So there are four substituents, that is for A, B, C, D. There are four substituents and vertical and horizontal bond. The center is called as a chiral center. So what is a chiral? So four different substituents, the four different atoms are connected with the center carbon atom is called as a chiral carbon. So Fischer projection, one is a vertical bond, another one is a horizontal bond. So the molecule is drawn in the form of two lines with the chiral atom at the center. So to make the Fischer projection, to view the chiral center, so that two substituents are coming out of the plane and two substituents are going back into the plane. So every cross and Fischer projection is a chiral center. So the horizontal bond are coming out of the plane of the paper, that is for towards the observer. So this is a horizontal bond, is coming out of the plane of the paper, that is for the towards observer, that is like curve. So coming out of the plane of the paper towards the observer is like curve, whereas the vertical bond going away from us. So Fischer projection should not be taken out of the plane, but it can be rotated 180 degree. So that is called as a Fischer projection. So example for Fischer projection. So this is an example for Fischer projection. So Fischer projection is with plus side. One is a vertical bond, another one is a horizontal bond. So and the center is called as a chiral center. So that the horizontal bond coming towards the observer is like that, whereas the vertical bond going away from us, that behind the screen. So that is called as a Fischer projection. And the next one is a Sahar's projection. So Sahar's projection is coming to, that is for staggered and eclipsed position. So rotating 60 degree. And this is called as an eclipsed position. and this is called as a staggered position. So this inverted Y. So this is an example for a Sahar's projection. It is a view of your molecule down, particular carbon-carbon bond. One is a front carbon, another one is a back carbon, are drawn using the stick at 120-degree angle. It's called as the Sahar's projection. It is a view of your molecule down, a particular carbon-carbon bond, and the groups connected to both front and back carbons are drawn using a stick at 120-degree angle. So this is a front carbon and back carbons are drawn using a stick at 120-degree angle, and view of your molecule down, a particular carbon-carbon bond, and groups connected to both front and back carbons and drawn at 120-degree angle is called as a Sahar's projection. So front carbon are staggered. That is, staggered means 60-degree apart. It's a 60-degree apart, and eclipse means it's a directly overlapping. So front carbon are staggered, this is 60-degree apart, and eclipse is a directly overlapping with a group on the back carbon. This is called as a Sahar's projection. So the advantage of Sahar's projection is to help better visualization of conformation of the molecule. So better visualization of that molecule, that is the main advantage of Sahar's projection. And it clearly depicts a three-dimensional geometry and interaction between the groups of adjacent carbon atom. And the third one is the Newman projection. So staggered and eclipse projections are called as Sahar's. And the third one, Newman projection. So for example, we are taking the ethane C2H6. So ethane is represented in many ways, that is like skeletal structure and condensed structure. And kettle and perspective. This is a perspective model. So CH2, this C2H6, ethane is represented is a skeletal structure or condensed structure or kettle structure or perspective. So all of this gives us useful information about the structure, but none of them is not explained the dihedral angle. But all the structures gives us useful information. For taking that example, we are taking that ethane, but none of them is explained the dihedral angle, but the Newman projection is explained the dihedral angle. Example for Newman projection. So there are three substituents in front carbon, another three substituents are in the back carbon. The same C2H6, we are taking an example is ethane. So the two carbon atoms, one is a front carbon atom, another one is a back carbon atom. So front carbon atoms are three substituents and back carbons are three substituents. So you have to calculate the dihedral angle, 60 dB. So rotate the carbon-carbon bond with the front and back carbon at 60 degree. So rotating. So we can get that dihedral angle is 0 degree. 0 degree dihedral angle. So Newman projection is a very rapid way to determine the specific bond angle. That is the main advantage of the Newman projection. So that are the three-dimensional structure, representation of three-dimensional structure. So the planar form, there are three important planar form. One is a Fisher projection, second one is a Sahar's projection, and third one is a Newman projection. So Fisher projection is one is a vertical bond, another one is a horizontal bond. And Sahar's projection is that one is a staggered position, another one is a eclipse position. So the molecules are drawn using a stick with the front and back carbon at 120-degree angle. And the Newman projection is why we have to use the Newman projection. So a very easy way to determine the dihedral angle. So for example, for the ethane, so many structures are there: skeletal structure, content structure, keppel structure, perspective structure, but no one is explained the dihedral angle. But if you go for the Newman projection, so the same ethane is represented in the Newman projection. So easily you have to use an easy way, a rapid way to determine the dihedral angle. So that are that a three-dimensional structure or representation of planar form. So far we have discussed about the organic molecule in isomerism, that is isomerism in organic molecules, and the second one representation of three-dimensional structure for the three planar form. So the organic molecule isomerism are chain, position, functional, metamerism, and the three-dimensional structures representation Newman, Fisher and Sahar's. Thank you guys.